Okay, so this is the application video for internal resistance and EMF. I should maybe write that on there. EMF and internal resistance. If you're a student of mine, then you may have these questions to hand. I might have emailed them to you, but if not, you can just press pause and have a go at them before I go through them. The whole point of this is that you press pause, you try and do the question, and then you press play as I go through it. So I'd have a go at question 1 first. If you want to do it part by part and press play each time, absolutely fine. If you'd rather do the whole thing and then watch the whole thing back, absolutely fine. Skip through if you need to. It's up to you. I don't know what you're doing. Enjoy. So this goes with all of the information that we just went through on our EMF and internal resistance video, which talked about the theory and also about the core practical. So watch that if you need to, because this is more just doing the questions. Right, a battery of EMF 9 volts and internal resistance R is connected to the circuit shown in the figure below. The current in the battery is 1 amp. Calculate the PD between points A and B in the circuit. So this is not just going to be about EMF and internal resistance, you can already tell, because often we have other parts of circuits in the questions as well. So here I need to work out the overall resistance for this part of the circuit. So I'm going to say 1 over R equals 1 over 2 plus 1 over 2, because these are in parallel. And that means that 1 over R equals 1. Half and a half is 1. Therefore, R equals 1 ohm. And I know I'm working out what the voltage is across A and B here. So I'm trying to work out this voltage here. But I've been told that the current in the battery is 1 amp. And if I've made this into an equivalent circuit of 1 ohm, without those, the current through that will also be 1 amp. So I'm going to do V equals IR equals 1 times 1 equals 1 volt. And there is my answer there. Calculate the internal resistance R. So what I want to do first is just draw my standard little diagram for internal resistance, which is this. And I need to have an overall equivalent resistance of the whole circuit. Now I've already worked out that these two bits in parallel are 1 ohm. So if I want to collapse my 1 plus 6 ohm resistors into 1, because they're in series, I just add them up. So I've got an equivalent resistance of 7 ohms there. So I'm going to use the equations, one of these equations here. I'm going to bring this back in. So I need to use E equals V plus IR, or E equals IR plus IR, or E equals V plus lost volts. There's lots of different things I can do. What I often do is I write down what I know and what I don't know, quite like Suvat. So I know that the EMF of this is 9 volts, and the terminal PD I haven't worked out yet. So I don't know. I know the current through the battery is 1 amp, and I don't know the internal resistance. I'm looking for that. And the big resistance R I've worked out is 7 ohms. So I want to use an equation that doesn't have big V in it, that just has E, I, R and R. So I'm going to be going for one of these ones at the bottom. And if I'm working out the internal resistance, I'll probably go for this one, because I don't want to have it trapped in a bracket. So E equals IR plus IR. I'm going to rearrange that. IR equals E minus I big R, and therefore, minus I big R, that's wrong. There you go. Therefore, I can say that little r equals E minus I big R divided by I. Sorry, there's not a lot of space on this sheet, so I can fit it all fit the whole thing on one page. And that's going to equal 9 minus 1 times 7 divided by 1, which is 9 minus 7 is 2 divided by 1, 2 ohms. Don't even need a calculator for that. So this one is 2 ohms, the answer there. Then calculate the total energy transformed by the battery in 5 minutes. Well, this is the equation that everyone likes to remember, which is that, no, it's not, that's a complete lie. The energy transformed by the battery in 5 minutes equals V over Q. Oh no, it is. I need to use that. So I know that voltage is energy per charge. Am I using that? I don't know if I am. I'm doing this completely cold. So E equals energy transformed in 5 minutes. I also know that, so I know that E equals V over Q. I also know that E equals PT. Aha, I'm not using that. So energy equals power times time, but I know that power equals IV. I'm going to say E equals IVT, and the current I know is 1 amp. I now know that the voltage across the battery, well, I know it's 9 volts. I know that because it's EMF. So 9 times time is 5 minutes, so 5 times 60. So 1 times 9 times 5 times 60, 1 times 9 times 5 times 60 is 2,700 joules. So there we are. Calculate the percentage of the energy calculated in part 3 that is dissipated in the battery in 5 minutes. So a good kind of hint here is that P equals I squared R is always the power dissipated in something. So for the power dissipated inside the battery, I'm going to say I squared little r. And I know that energy equals power times time. So instead of writing E equals IVT, I'm going to write E equals I squared RT. So E equals 1 squared times the resistance, the internal resistance, which I've worked out is 2, times 5 times 60, which is the number of seconds in 5 minutes. So 5 times 60 times 2 times 1 squared, which is 1. I get 600 joules. But it's asked us for a percentage, so I need to work out what 600 joules is as a proportion of 2,700. So I'm going to do that sum divided by 2,700 and then times by 100. And I get 22%, which seems reasonable. State and explain one reason why it's an advantage for a rechargeable battery to have a low internal resistance. Well, we talked about in the previous video that the here we go. We've got this equation. If I have a high internal resistance, then I'm going to have a lower terminal PD because it's going to have more of an effect the higher the current. So I want to make sure that a low internal resistance means a higher terminal PD as less volts are lost due to little r, because E equals V plus IR. So that's one thing you could say. You can also say that the internal resistance is going to limit the current because it's a resistance, so it's going to make the current smaller. Also, the higher the internal resistance, the more energy is wasted. So the low internal resistance means you're going to waste less, because this is dissipated, this is wasted energy here. You're going to waste less energy. Okie doke, question 2, annoyingly, as you can only see half of it. So have a go at this first part of question 2. And then, oh, you know what I can do? I can be clever. I can move the page. Who'd have thought? I didn't think of this massively when I set up my little station, but you know what? I can fold this. Here we go. Sure that's visible? Yeah, it looks visible. Right, question 2, press pause, have a go, and then press play when you're ready to go through it. Okie doke. Question 1, what is meant by the EMF of a battery? Be careful, don't just say it's a perfect voltage or the voltage gained. The EMF, by definition, is the energy transferred per unit volt from another 2 electrical energy. It's the 2 electrical energy bit that's important. No, sorry, that's completely wrong there. Per unit charge. I'm very tired. Should probably wait till tomorrow to this, but there we are. So the energy transferred per unit charge to electrical energy is the definition. When the switch S is open, the voltmeter, which has an infinite resistance, reads 8 volts. When the switch is closed, the voltmeter reads 6 volts. Determine the current when the switch is closed. Now, important point, when the switch is open, we want voltmeters to have infinite resistances. That is right. That is as if we have a voltmeter just across the battery in not a circuit. So that means that the EMF of this circuit is 8 volts. Because when the voltmeter is across it and there's no current running through it, we get a voltage of 8 volts. Therefore, the voltmeter reading 6 volts is the terminal PD. So that's when there's a current running through it. and they want to work out the current in the circuit when the switch is closed. Now, if there's 6 volts across the voltmeter, that voltmeter is reading across the battery and also across that resistor. So the voltage across the resistor is 6 volts too, because if I gain 6 volts in the battery, I lose 6 volts in that resistor. I'm just going to use the equation V equals IR, but for this resistor. So I equals V over R. I know the voltage across it is 6 volts, and then I divide that by 2.4 ohms. And 6 divided by 2.4 comes out as 2.5 amps, which is correct. Okay, so I've got 2.5 amps. Then we've got show that little r is 0.8 ohms. So like I did before, I'm just going to write out the things that I might need to know. So I know that EMF is 8 volts, and I know that terminal PD is 6 volts. I've worked out that current is 2.5 volts, and I know that the external resistance is 2.4 ohms, and I want to know the internal resistance. So I can go for any of them here, really. So I'm going to go for the equation E equals V plus IR, the classic one. Therefore, I can say that E minus V over I equals R. And that means that R equals 8 minus 6 divided by 2.5, which is 2 divided by 2.5, which is 0.8 ohms. Oh, look, there we are. Show that it equals 0.8 ohms. The switch S remains closed. Calculate the power dissipated in the 2.4 ohm resistor. So generally, power dissipated is, like I say, that equation P equals I squared R, and they care about the 2.4 ohm resistor. So the current I know is that shouldn't be a V, that should be an A, is 2.5 amps, and then the resistor is times 2.4 squared. So 2.4 squared times 2.5 equals 14.4 watts. Oh, I've done the wrong way around. Sorry, 2.5 squared times 2.4. 2.5 squared times 2.4. It's a very close answer, but not quite right, which is 15 watts. The total power dissipated in the circuit, I need to think about that. Plus, I'm going to dissipate some power in the internal resistor here. So P equals I squared little r, which is 2.5 squared times, I've now worked out 0.8. And that is 2.5 squared times 0.8, 5. So I do 15 plus 5, because it's the power dissipated across the big resistor plus across the little resistor. 5 plus 15 equals 20 watts in total. And then the energy wasted in the battery in 2 minutes. Well, energy equals power times time. And the power I'm wasting in the battery is from the internal resistance. So that is going to be 5 times 2 minutes is 2 times 60. So that's 10 times 60 is equal to 600 joules. So there we are. Question 2. Question 3. Here it is for you to have a look at. Just let me check that you can read that. Yeah, I think you can. So press pause if you need to, have a go, and then come back when you're ready to go through it. Okie doke. So we want to work out the total current in this circuit. Now I'm going to use for this the equation V equals IR, and realise that I can always use this equation as long as I have the same subscripts. So I'm going to say the total voltage equals the total current times the total resistance. Now, we're told that each of these resistors have got a resistance of 30 ohms. So the total resistance in this circuit is 30 plus 30, plus there's an internal resistance there of 2. So I can say that the total resistance is 62 ohms. And then I'm going to work out the current by saying IT equals V divided by R, which is going to be 12 volts divided by 62. And 12 divided by 62 is 0.19 amps. Okay, 0.2 is not rounding that very well. I know it is, that's a lie, but I'm going to write 0.19. Right, the voltage between points P and Q. Okay, now this is a series circuit, so if I know the current anywhere, I know it everywhere. So I'm going to say V equals IR, And between P and Q, the resistance is 60. So I'm going to do I, which is 0.19, times 60. And I get 11.6. So the voltage across P and Q, or across A and B together, is 11.6 volts. Then I've got the power dissipated in resistor A. It's dissipated, we're seeing a pattern here, P equals I squared big R for A. And the current is series, so it's the same everywhere, so 0.19 squared times 30. So 0.19 squared times 30 equals 1.083 watts. So I'd write that as 1.1 watts generally. And then part 4, the energy dissipated by resistor A in 20 seconds. Energy equals power times time equals 1.083 times 20 equals 21.66 joules, so 22 joules. So quite an easy question there. Not a lot about internal resistance in there, just the fact that we need to include it in our total resistance there. Question 4, which we'll have a look at now, is, let me just fold this one over as well, all the folding. So prepared. Here we go. So question 4, have a read, have a go, and then press play when you're ready to go through it with me. So a battery is connected to a 10 ohm resistor as shown in the diagram below. The EMF of the battery is 6 volts. Define EMF. So once again, I'm going to say it's the energy per unit charge transferred to electrical energy. Okay, a PD, remember, is when I've got an energy that's transferred from electrical energy. When the switch is open, the voltmeter reads 6 volts. And this is becoming a common thing. When the switch is open, I get a different reading to when it's closed. And it's asking me to explain why. Well, when the switch is open, the voltmeter reads the EMF. When the switch is closed, I'm so sorry for my terrible handwriting because I'm writing in a really funny angle to fit it on the video. When the switch is closed, a current runs through the cell or cells. So the internal resistance of the cells causes some voltage to be lost. And that will get you both marks there. So 5.8 is the terminal PD, 6 volts is the EMF. And they've asked us to calculate the internal resistance of the battery. So I'm going to do that same thing as I did before, write down all the things I might know. So EMF I know is 6 volts because it's when the battery switch is open. Terminal PD is 5.8. It's always less than or equal to the EMF. The current I do not know. The external resistance is 10 ohms and the internal resistance is what I want to find out. Question mark. So I've got 2 unknowns here, and if I look at my my equations, that's not particularly helpful because I don't have any equations that can cope with that. Here they are. But what I can do is I can work out the current. So the current is equal to V over R, where V is the terminal PD and R is the external resistance, 10 ohms, because we're going to have the same voltage across this here. So 5.8 divided by 10, I can do this in my head, but I'm going to use the number anyway, so I may as well keep it there, equals 0.58 amps. So now I know everything that I need. To work out the internal resistance of the battery, I'm going to say E equals V plus IR. Therefore, R equals E minus V over I equals 6 minus 5.8 divided by 0.58. And that is 6 minus 5.8 divided by 0.58 equals 0.34 ohms. There we are. State and explain why it is important for car batteries to have a very low internal resistance. Now, this is kind of you having a bit of knowledge about what starter motors and car batteries need. But a car battery or car, I don't really think about how to say that. For a car to start, a very large current is needed. A high internal resistance, I'm going to call it little r, would limit this, so it needs to be as low as possible. And once again, I'm sorry for the absolute terrible handwriting, it's not how I normally write. Okie doke, question 5. Let's move this one out of the way and let's keep on going. So have a go at this one. I'll check you can see it. And then press play when you're ready to get some answers. So we've got a car battery has an EMF of 12 volts and an internal resistance of 9.5 times 10 to the minus 3 ohms. And when the battery is used to start a car, the current through the battery is 420 amps. Calculate the voltage across the terminals of the battery when the current through the battery is 420 amps. So I've got an EMF, an internal resistance, a current, and they're asking for the terminal PD. So nice and simple, E equals V plus IR, therefore V equals E minus IR. V equals 12 minus 420 times 9.5 times 10 to the minus 3. I'm going to do that a little bit first. So 9.5 times 10 to the minus 3 times 420. And I'll do 12 minus that, and I get 8.01 volts, or 8.0 volts. Then we've got the copper cable connecting the starter motor and to the battery has a length of 0.75 metres and a cross-sectional area of 7.9 times 10 to the minus 5 metres. The resistance of the cable is 1.6 times 10 to the minus 3 ohms. Calculate the resistivity of the copper, giving an appropriate unit. So nothing to do with internal resistance, but they like to do this. Rho equals RA over L. That's resistivity equals resistance times cross-sectional area divided by length. So we've got a resistance of the cable here is 1.6 times 10 to the minus 3. We're told the cross-sectional area. Often they give you the diameter there, so making life a little bit easier here. And the length is 0.75 metres. So if I do that sum, so 1.6 times 10 to the minus 3 times 7.9 times 10 to the minus 5 divided by 0.75, I get 1.6853 carrying on times 10 to the minus 7. So I'm going to write 1.7 times 10 to the minus 7, and then for resistivity, the unit is ohm meters. So that is question 5. Question 6. Lots of folding still. There's loads of questions to go. I don't know how much longer I'll cope on the video, but we'll see how we go. Here we go. Hopefully starting to see some patterns. Press pause, have a go at these questions, and then press play when you're ready for me to go through the answer. Okie doke, so here explain what is meant by the EMF of the battery. It's the energy transferred per unit charge to electrical energy. This time they also let you said the PD when there's no current, but that is a description more than a definition. And explain what is meant by the internal resistance of the battery. And there's lots of things you can say here. One thing you can say is the resistance due to the materials within the battery. Or they let you say lost volts per unit current, and that comes from R equals V over I. And remember, it's the lost volts that make the resistance, internal resistance happen. Right, the battery is used to provide the starting motor of a car with a current of 800 amps. Calculate the potential difference across the terminals of the battery. So we've got an EMF of 12, we've got an internal resistance of 5 times 10 to the minus 3, we've got a current of I, and they want to know V. So once again, E equals V plus IR, but rearranged. V equals E minus IR. V equals 12 minus 800 times 5 times 10 to the minus 3. Let's do that as a calculator. 800 times 5 times 10 to the minus 3. 12 minus answer equals 8, which is the correct answer, which is good to know. And then part 2, calculate the rate of dissipation of energy due to internal resistance stating an appropriate unit. So once again, P equals I squared R is the equation for dissipation. And we've got a current, the current is 800, so 800 squared. We've got an internal resistance, it's 5 times 10 to the minus 3. So 500 squared times 5 xp minus 3 is 1250 watts. And the thing about, what have I done here? Let me just try that sum again, because I'm doing the right sum, but it doesn't seem to match with the answers. No idea what happened there. Calculation error, clearly. 3,200 watts. Because a rate of dissipation, that's a rate of energy, and power equals energy over time. So they just mean what is the power? That's the question. State and explain the effect of attempting to use a battery with a much higher internal resistance to start the car. So you see they really like this one. So this is the idea that if you've got a higher internal resistance, you won't get enough current or power, because you'll have lost more power, because you'll have more power dissipated. So you won't get enough current or power, so car probably won't start. So they do like a car question, it would seem here. Right, moving on to question 7. I like this one because we're going to think a bit about the core practical. There is a few parts of this. We're going to start with question 7's part A and B, and then we'll do the rest. So have a go at this bit first. Press pause and then press play when you're ready to carry on. Okie doke, so we've got a cell of EMF, an internal resistance R is connected to a variable resistor. We've got a current through the cell and a terminal PD of the cell is measured, and we get an equation. And this is just like, if I can find the page, everything we talked about here. Okay, it's the core practical. So explain why the terminal PD decreases as the current increases. So you could use the equation here, E equals V plus IR. So why does the terminal PD decrease as current increases? Well, EMF and R are fixed. Therefore, increasing I means more volts are lost. So terminal PD decreases. And in terms of my little dots that I like, it's that. I do like a few dots to explain things. Use the graph to find the EMF E of the cell. Now we know from here, this is something you should just know, that the EMF is the y-intercept. So I'm going to read that y-intercept off. This is 1.4, each of these is 0.4, so that's 1.44, 1.48, 1.52 volts is going to be my answer there. Now, you might need that part of the question for the next bit. So it says, use the graph above to find the internal resistance R of the cell. So let's fold this one over so we can have the two together. Like so. Okie doke. So have a go at these parts if you are using the video to do these questions. And press play when you're ready to carry on. So use the graph above to find the internal resistance R of the cell. Well, we know from this bit here, the EMF is minus the gradient. So I'm going to work out the gradient. Generally, if you get given a graph and you're working out the gradient, there's something wrong. And that gradient, I'm going to go from the top up there to here. So it's the change in y divided by the change in x. The change in y is 1.52 minus, at that point there, 0.2. And x is 3 minus 0. I know it's hard to do it on a video, so I would understand if you can't quite read that. Divide that by 3, and I get that the gradient is 0.44. It should be minus because I've done these the wrong way around. So it should be 0.2 minus 1.52, but we'll cope. And there is your answer, 0.44 ohms. You're allowed anything between 0.44 and 0.46. You are doing it from the computer screen, so if you get something slightly different, I think it's understandable. Right, draw a line on the same graph that shows the same EMF, but double the internal resistance of the first cell, labelling your graph A. Now, if we know that EMF is y-intercept and gradient is minus R, I need to have the same C and double the gradient. So it's going to be twice as steep. So it's going to look something like this. Okay. I haven't been very scientific with that, but you should have half the gradient. I think it's actually about right. So that's going to be A. And then we've got the same EMF, but negligible internal resistance, and label that graph B. Well, if we haven't got much internal resistance, then I'm going to write this down. E equals V plus IR. Well, if R is basically 0, I can get rid of that and I get that E equals V. So I should get, with no change, that should be a horizontal line. So I should get a flat horizontal line because that's not changing over time. That's a terrible line. Please ignore it. In the original circuit shown in part A, which is here, the variable resistor is set to a value such that the current through the cell is 0.89 amps. Calculate the charge flowing through the cell in 15 seconds, stating an appropriate unit. So this is nothing to do with internal resistance. We're going to just use the equation I equals Q over T. Therefore, Q equals IT equals 0.89 times 15. So 0.89 times 15, I get 13.35 amps. Not amps, coulombs, because this is charge. And then final bit. See, so many more questions. I think we're nearly done. Calculate the energy dissipated in the internal resistance of the cell per second. We know the drill now. P equals I squared R. The current, we're told, is 0.89. Don't forget to square it, my common mistake. And the internal resistance of the cell, we were told, we worked it out, didn't we, is 0.44. Or 0.45, or 0.46, whatever you got there. So 0.89 squared times 0.44, I'm getting 0.35 watts, which is the correct answer. Okie doke. Right, question 8. I think there's like 5 more. We may stop earlier. I might go mad. But it's good. You start to see the same thing over and over again, which is really useful. So here is question 8. Feel free to press pause and have a go at it, and then press play when you want to carry on to go through the answer. Okie doke. In the circuit shown in figure 1, the battery has an EMF of 6 volts. When the switch is closed and the lamp is lit, the reading on the voltmeter is 5.4 volts. That's the terminal PD. Explain without calculation why the voltmeter reading is less than the EMF of the battery. We've already talked about this, haven't we? But the battery has an internal resistance when current passes through. Voltage is lost due to this. Okay, so similar question to what we've had before. We've got a torch is powered by 2 identical cells, each having an EMF of 1.5 volts and internal resistance of R. The cells are connected in series. The bulb is rated at 1.6 volts and the voltage across it is 2.5 volts. Draw the circuit described. So we want to have 2 cells in series and 2 little resistors for internal resistance, and then the bulb. So I'm going to draw cell, little r, cell, little r, bulb, like that. That works. Yeah. Calculate the internal resistance of each cell. The voltage across this is 2.5 volts. And we know that 2.5 volts is the terminal PD. EMF is 1.5, so EMF of both is going to be 3 volts. and the internal resistance is going to be 2R totally. And we know that, okay, so the torch bulb is rated at 1.6 watts. Now, what the point of that, is that meant to be 1.6 watts, or sometimes they do 1.6 ohms? Just let me look at the answer. No, they do mean watts. Sometimes you get an ohm sign, becomes a W when you put it into Word, because omega is a W. Right, so we've got a power of 1.6 watts. So why will that be useful? Well, think about power equals current times voltage. So I can work out the current by saying I equals P over V equals 1.6 divided by the voltage across that, which is 2.5. So 1.6 divided by 2.5, I get 0.64 amps. So now I've got E equals 3 volts, I've got 2R, I've got I equals 0.64 amps, and they want to know little r. Oh, and I know that V is 2.5 volts. So I can use E equals V plus IR, but rearrange that. So R equals E minus V over I equals 3 minus 2.5 divided by I, which is 0.64, which is 3 minus 2.5, which is 0.5, divided by 0.64. I probably could have done that first bit on my own, but there we are. Equals 0.78 for 2R. Remember, this is the two of them together. So 1R is 0.78 divided by 2, which is 0.39 ohms. Then we've got part C. Here we go. In the circuit figure 2, the cell has an EMF and internal resistance R. The voltage across the cell is read on the voltmeter and has an infinite resistance, and the current I through the variable resistor is read on the ammeter. Oh look, it looks very similar to our core practical. By altering the values on the variable resistor, a set of V and I is obtained. These values, when plotted, give the graph as shown. Show how the values of E and R may be obtained from this graph. Explain your method. So we are trying to explain this. Okay, how do we know what things are? So I can say that EMF equals the y-intercept, and that R equals minus the gradient. And I can try and show that with y equals mx plus c, but y is v and x is I. And I'm going to compare that, CF means compare with, E equals V plus IR, and I get that V equals minus RI plus E. So these must equal each other. Right, question 9. Oh, we're nearly done. There's only 11 questions, so we're nearly there. 2 more to go, and they're getting easier because they're just the same thing over and over again. So hopefully we're finding this more and more simple as we go. Sorry, I've now messed all of my paper up. Completely out of whack. Here we go. So question 9. Press pause if you need to and have a go at that one. Press play when you're ready to carry on and go through the answer. Okie doke, so we've got the same thing again. EMF, internal resistance, blah, 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 core practical. The EMF is related to V, I and R by the equation E equals V plus IR. Rearrange the equation to give V in terms of E, I and R. So basically V equals E minus IR. In an experiment, the value R is altered so that the values of V and corresponding values of I are obtained. Using the axes, sketch the graph you'd expect as R is changed. We know it is this because it's the core practical, and we know that E is the y-intercept and R is the negative gradient. Don't just say the gradient, it is the negative gradient. Be careful there. So that was nice and easy, wasn't it? So 2 to go, question 10. Press pause and have a go at the question if you need to. Otherwise, we'll carry on and go through the answers. So we've got the circuit in the diagram below contains 4 identical cells, A, B, C and D, each of EMF, 1.5 volts and negligible internal resistance. Therefore, this question has probably nothing to do with what we need to do, but oh well, let's do it anyway. And the resistance of each resistor is 4 ohms. Calculate the total resistance of the circuit. So step 1 is I want to collapse. So this is 4 ohms. I want to collapse these two into a single resistor here. So that's going to be, this is 4 and 4, 1 over R equals 1 over 4 plus 1 over 4. So 1 over R is going to equal a half. A quarter and a quarter is a half. Therefore, R is equal to 2 ohms. And then the total of these ones, if I add them into one, is going to be 4 plus 2, which is 6 ohms. Calculate the total EMF, the combination of cells. So this kind of brings up, how do we cope with EMF in things that are parallel? So EMF, normally we just add them up. So we'd have, this is 1.5, this is 1.5, and then these are each 1.5. But this is in parallel, so the electrons are going to go through this, and then through, they're going to go through D, they're going to go through C, and then they have to either go through A or through B. So each electron is only going to go through 3 cells. So the total EMF is 3 times 1.5, which is 4.5 volts, because they can't go through both. Calculate the current passing through cell A. Okay, so cell A, we're going to do V equals IR. Okay, now we know that V in cell A is going to be, hang on, no, I'm not going to do it that way. I'm thinking of a different way. I'm going to do VT equals IT RT and say that the I'm going to think about the whole voltage here of all of these cells together. And I'm going to say that that means that the total current equals VT over RT. And I've worked out the total voltage, it's 4.5, and I've worked out the total resistance, it's 6. So 4.5 divided by 6 is equal to 0.75 amps. So that's the current going through here. Then the current's going to split to go through either through cell A or through cell B. So I just need to do 0.75 divided by 2, which is 0.375. Yeah, to get the current through A or B, because they have to split at that point. Calculate the charge passing through cell A in 5 minutes, stating an appropriate unit. So charge, we're going to say that Q equals IT. I've got a current there, it's going to equal 0.375. The time is 5 minutes, which is 5 times 60 seconds. We get an answer of 112.5 coulombs. That is the appropriate unit. Each of the cells can provide the same amount of electrical energy before going flat. State and explain which 2 cells in the circuit you would expect to go flat first. Would it basically be A and B or C and D? So have a think, and you have to explain why. C and D will go flat first because all the charge passes through them. So they will give out their energy, all of their energy, more quickly. A and B, because only half the charge is going through them, they're going to last twice as long. Let's say that each of these bulbs has got 100 joules of energy, and they're giving out a joule every minute. A joule per coulomb, let's say. So it will only take 100 coulombs to get through. After 100 coulombs have passed through D and delivering out, but it's going to take twice as long for 100 coulombs to pass through A and B because they're splitting up, essentially. So yeah, that had nothing to do with EMF, but there we are. Question 11, though, definitely does have some stuff to do with EMF. And look, once again, it is the core practical. So final question, can you tell I'm slightly losing the will to live? This is now 43 minutes long. A battery of EMF E and internal resistance R is connected in series to a variable resistor R and an ammeter of negligible resistance. A voltmeter is connected across R as shown in the figure below. State what is meant, guess what, by the EMF of the battery. And it is the energy transferred per unit charge to electrical energy. Okay. The reading on the voltmeter is less than the EMF. Explain why this is so. A current, always that, is running through the cell, causing volts to be lost due to internal resistance. Everyone's favourite question. A student wishes to measure E and R. Using the circuit shown in the figure above, the value of R is decreased in steps, and at each step the recordings of V and I on the voltmeter and ammeter respectively are recorded. These are shown in the table. Give an expression relating V, I, E and R. E equals V plus IR. Draw a graph of V on the y-axis and I on the x-axis on the graph paper. I don't have any graph paper, it will look like this. And then determine the values of E and R from the graph explaining your method. E is going to be the y-intercept and R is the negative gradient. And the y-intercept is 9.2 volts plus or minus 0.1 volt if you decide to have a go at the question. And the gradient, therefore minus gradient, is 14.2 ohms. And you're allowed anything between 14 to 14.3 ohms as your answer. But I am not drawing that graph out now. Right, that was a lot of questions. Hopefully you could start to see the patterns that came up over and over again, and hopefully EMF and internal resistance is a little bit clearer.